Okay, 5.2, definite integrals. So Riemann sums or Riemann sums. Um, Riemann sums are LRAM, RM, and AMRAM. Or rather, these are examples of Riemann sums. They do the same thing. They partition an area under the curve, and then they add them up. Okay, Riemann sums is a formal notation for integration, but it's not the one that we mostly use. Next class, I'm going to give you some problems, and I'm going to want you to change this into this notation here. This is, what's his name? Leibniz. This is his notation. We like this notation. This is the friendly notation. Because the Riemann sums, or Riemann sums, they look really, really complicated, but they're doing the same thing. Um, delta x is the change in x, that's dx. This right here is basically our function. Oh, got it right there. Um, this Greek letter sigma means sum. We're adding up all these partitions. Well, this right here is just an elongated s that stands for sum. The k equals 1 to n, that's just basically all the x values. You would start with the first one and move up to however many they want you to count. Well, in Leibniz, it's just a and b are your intervals. So that's the one we're going to use. Okay, definite integrals, and this is the breakdown. This is the notation we're going to use mostly. I mean, it is important to know how to write, or rather rewrite this. We want to know how to rewrite this in this form, right? And we'll do that next class a little bit. So, but here, as you can see, the function, right, is the integrand. Dx is the variable of integration. That's the variable we're deriving in respect to. Just like we, or not deriving, sorry, integrating with respect to, just like we derive with respect to x. Let's see, b is the upper limit, so it's the higher x value. A is the lower limit, it's the lower x value. The integral sign, of course, is just an elongated s. And then the overall thing is called an integral. And it is said, just as it says, when you find the value of the integral, you have evaluated the integral. Oh, I'm thinking of something else. The way you would read this is the integral of f of x from a to b with respect to x, or the integral of f of x from a to b dx. All right, example 1. We're going to revisit the train problem. The train moves along a track at a steady constant rate of 75 miles per hour from 7 to 9. What is the total distance traveled by the train? The only reason I want to revisit this is because I want to show you that this can be rewritten. Not only just to find the area under the graph or under the straight line there, but it can be written as an integral. Okay, so the integral, this is the integral notation, right, from a to b of my function with respect to x. So that's notation. Now a to b, those are my intervals. So I could use from 7 to 9. That's perfectly fine. From 7 to 9. Oh, that's a 9, not an A. Holy crap. 7 to 9. Okay. My function. Now remember, the 75 miles per hour was a straight line. How do you write the equation of a straight horizontal line? Well, this right here, if this is 75, the equation of this line is y equals 75. 75 is my function. So 75, and then I am deriving with respect to x, even though there is technically no x here. And this is how we would write it, and my answer to this would be the area. Okay, so like if this is 7, this is, let me change my mind. If that's 7, this is 8, and this is 9. My answer would be the area. It's here, right? Which was 2 times 75, which is 150. Okay? All right, proceeding. Example 2, sketch a graph of the function and evaluate the integral. All right, so I want you to sketch the function. So this is an absolute value, and if you recall, an absolute value looks like a v. They want me to pay attention to the interval from -2 to 1. Okay, so here's -2, and here's 1. Okay, so let's see. I plug in -2, I get +2. Oops, I wrote that in the wrong place. Oh my goodness. It is the end of the day for sure. So I plug in -2, I get +2. I plug in -1, I get +1. If I plug in 0, I get 0. If I plug in +1, I get +1. If I plug in +2, I get +2. Now remember, the graph looks like a V. Okay, they want me to pay attention to the part of the graph that is from -2. Wow, that is off. Oh, I'm sorry. Don't judge my drawing skills here, peoples. Let's just pretend that this was actually in the right place. Okay, so -2, and they want me to go all the way to 1. So here's 1. So this is the area that I'm going to find. If I find that area, this will be the answer to my integral. This is what I'm evaluating. All right, now these are triangles, yes? So area of a triangle, in case you forgot or don't remember, but you do need to know this formula, is half base times height. Remember, a rectangle is base times height, but a triangle, if you really think about it, right, I got a rectangle, it's base times height. A triangle is half of a rectangle, so half base times height. Okay, so to evaluate this, all I got to do is find the area of this big old triangle and find the area of this itty bitty little triangle. So let's see. Let's do the big one. So that's 1/2 times the base. Let's see. My base is this right here, which is supposed to be -2 or 2, right? No such thing as negative lengths. And then my height is this here, and this was also 2. So there's the big triangle. And then the small one, 1/2 times, let's see, this is the base of my small triangle, it's 1. And then the height of my small triangle is also 1. And so if I actually do the math here, this is the answer to my integral. So let's see, 2 times 2 is 4, divided by 2 is 2. And then 1 times 1 is 1, divided by 2 is half, or 0.5. So my answer is 2.5. Oh. B. I want you to graph this, find the area as well. Okay, so I want you to become familiar with equations that look like this. Okay, this equation is essentially this: y equals square root of 9 minus x squared. Okay, let's say I get rid of the square root by squaring both sides. I square this, and I square that. I get y squared equals 9 minus x squared. Add the x squared to both sides, and I end up with x squared plus y squared equals 9. If you recall from Algebra 2, from geometry, even from pre-calculus, this right here is the equation of a circle, centered at 0, 0, with a radius of 3, because this was r squared. Okay, so then that means that this equation right here is the equation of a circle. Now technically circles are not functions because they don't pass the vertical line test. But when you manipulate it this way, it actually does end up being a function because you end up with only just a semicircle. Because no matter what number of x we put in, it's just going to stay on top. It's going to be positive. So, all right, so back to the picture at hand. So let's see. They want us to go from -3 to 3. So here's -3. Here's +3. So let me plug in. I plug in 0. I get 9 minus 0. So that's the square root of 9, which is 3. So, all right, so where was I? I plugged in 0, and I got 3 back out. I plug in -3, and I get 9 minus 9, so it's 0. The square root of 0. I plug in +3, and I get the same thing. So this is what this looks like, roughly. Okay, not a perfect semicircle, sorry. Now I need to find the area of all of this here. So remember, this is basically half of a circle with a radius of 3. If I want to find the area, all I need is the area, the formula for area of a circle. And that is pi r squared. But since this is a semicircle, times 1/2. So 1/2 times pi times r squared. And r is my radius. My radius is 3. So times 3 squared. And then that is times 9, which is 9 pi over 2. And there's my answer. Example 3. Consider the function f of x equals 3 minus x. Sketch a graph of this function. Okay, so for part A, what is the area between the curve and the x-axis between x equals 2 and x equals 7? So first I'm going to graph the function. So let me move this a little bit. Right there's good. I am going to go ahead and do a table. So x and f of x. And then, so since I'm going from 2 to 7, all I really need is from 2 to 7. So 2, 3, 4, 5, 6, 7. And then if I were to plug all of those in, I would get 1, 0, -1, 2, or sorry, -2, -3, and -4. All right, let's see. Let me go ahead and label this graph. Wow, I suck. Let me try that again. Hee hee. All right. So here's 7. 1, 2, 3, 4, 5, 6. 1, 2, -1, -2, -3, -4. All right, that's good. Okay, so in order to find the area, I need the graph. And so 2, 1, 2, 1, here it is. 3, 0, 4, -1, 5, -2, 6, -3, and 7, -4. So there it is. It's a straight line. Bear with me here, folks. I'll try to make that as straight as I possibly can. That's close enough. All right, so I need to find the area underneath the curve. But, so this is underneath. So I need this little area right here. And that's in the shape of a triangle. I can find that because we just did that, right? This area is 1/2 base times height. The base is 1, the height is 1. So it's 0.5 or 1/2. I don't care what you call it. Now, the area is always, I call it under the graph, right? It's under the graph. But as you can see, part of this graph is below the x-axis. So the way you're going to do the area is you're always going to work your way towards the x-axis. Okay, see how the little blue triangle goes down towards the x-axis and then it stops? Well, for the rest of it, I'm going to work my way up to the x-axis. And then I'll stop. So now this is the shape whose area I have to find in order to evaluate my integral. Okay, so I do have 2 triangles, but one of them is above the x-axis and the other one is below. Now, remember the derivative and what happens when the original function is increasing. Well, then we know that the derivative is positive. When the original function is decreasing, we know the derivative is negative. Well, here, it's the same idea, kind of. But if it's above the x-axis, right, we consider that positive. Well, if it's below the x-axis, we still consider that negative. So, although it's kind of hard to accept, whatever area this triangle is, we're going to treat it as being negative. Okay? Negative area. So the area and it's negative because it's below the x-axis. Please write this down somewhere. Any area below the x-axis is going to be negative no matter what. So the area here is 1/2 times the base. So this is the base, let's say. So that's 4 times height. And this is also 4. So 4 times 4 is 16 times 1/2. That's 8. So now here my area is 0.5 plus or minus, however you want to call it, -8. Okay? This area here is -8. Okay, this is -8. I need my area to be negative. Okay, making my answer -7.5. All right, part B, evaluate the integral of 3 minus x from 2 to 7 dx. Okay, so I'm just rewording basically this function and the fact that it's from 2 to 7 with an actual integral in integral notation. And so then, of course, my answer is going to be the area that we found above, -7.5. All right, next, example 4. Given given the integral of sine of x from 0 to pi dx equals 2, evaluate the following integrals. First, I want you to go ahead and draw what sine even looks like. If you remember what sine looks like, it's really important for us to know what these graphs look like. So for the given here, the given information, let's recall that sine looks like this. I'm going to go ahead and take, this is pi, this is 2 pi, this is negative pi, this is negative 2 pi, and sine looks like an S. Let me do it in green. Sine looks like an S, and then it keeps going, right? Okay, now they're telling me that from 0 to pi. So from 0 to pi, so this area right here is 2. Okay, so logically, the area in here and here is also going to be 2, but because it's below the x-axis, it's -2. And the area up here is also going to be 2. I suddenly am thinking of watermelon. Wonder why that is. All right, so A, they want me to find or evaluate the integral of sine of x from pi to 2 pi. Let me sketch that out. Okay, you have space. It doesn't kill you. Make these sketches. They'll help you understand. Okay, so from pi to 2 pi. So pi, 2 pi, this is 2 pi, this is pi. And then let me draw my sine. So da-da, up, and then down. So from pi to 2 pi is here. Now remember what I said. If this area, back over here, we're back over here. Back on this picture here. If this area is 2, then it makes logical sense for the area down here to also be 2, but it's negative. So the answer for A is -2. All right, B. We're going to do the same thing. I'm going to draw it. I'm drawing it. It's good to draw. Imagine that straight. Pretend. From 0 to 2 pi again. I mean, from 0 to 2 pi. It's not again, sorry. Let me draw my pretty little, and then like this, and then like this. They want me to focus on from 0 all the way to 2 pi, so all of this area. Now recall, this is 2, this is -2, so guess what? My answer is going to be 0. They cancel each other out, because 2 plus -2 is 0. C. They want me to go from 0 to pi over 2. Okay, so let's call this pi, -pi. I'm going to go ahead and draw the whole thing. Okay, now pi over 2 is going to be right there. They want me to go from 0 to pi over 2. So this is the area I need. Now, if you recall, the entire, what do you want to call this? It kind of looks like a semicircle. The whole thing is 2. Pi over 2 is right dab in the middle. So instead of 2, this area is going to be half of 2, which is 1. That's my answer. All right, D, last but not least. I'm going from -pi to pi. So -pi to pi. And let me go ahead and draw my pretty little sine function. Ooh, that's horrible. Okay. And they want me to focus on all of this. So again, remember this is 2. And remember, because this is underneath the x-axis, it's -2. So a big fat 0. All right. E. So I'm going from 0 to pi. Let's call this pi. But there's a shift. That 2 is telling me that I have to move up 2 spaces. So normally, sine would be located here. But since I have to move up 2 spaces, I'm going to end up here. So then, let me give myself a little line here so I can do my curves all pretty. So it's now going to look like this. Now they want me to focus on the area from 0 to pi. So from here to here. Now, this right here does not change. This is 2. But see, what's interesting about this problem is now that I also have to find this area. It's a rectangle. Okay, I can find that, no problem. How wide is it? Pi. Times how tall is it? Remember, this right here is 2, because I had to move up 2 spaces. So this area is 2 pi. So for this one, my answer is 2 plus 2 pi, or 2 pi plus 2. All right. Integrals on the calculator. So you can actually evaluate integrals on the calculator, but obviously you have to know how to do it by hand because you're not always allowed to use the calculator. But this is good for really hard-looking integrals because they're usually on the part where you can use the calculator. They don't expect you to do it by hand. But then if you don't remember that you can do it on the calculator, you know, that would suck. So evaluate the integrals numerically with a calculator. Okay, on your graphing calculator, you're going to hit the math button. and then you're going to select number 9, and then you're going to end up with something that looks like this on your screen. This is actually dotted. Let me make dots. And then parentheses, another dotted box, close parentheses, and then a D, and then another dotted line or box. And then you're going to fill in. Obviously, here's the function. You're going to put x here, and then here are going to be your limits. So if they told you from x equals 1 to x equals 4, then you put the 1 there and then the 4 there. Okay, so I'm going to show you real quick. So example 5. And there's my calculator coming up. I'm going to go ahead and do example 5. I'm going to evaluate it on the calculator. Just have to hit math. Alright, so let me go ahead and clear all this stuff. Well, let me make sure it's in the screen first. Hold on. Okay, so hit math. And then you're going to scroll down to where it says 9. It says fn int. So that's just the integral. Okay, so number 9. And then that's what pops up. And so for example 5, sorry, my limit is from 1 to 3. So I'm going to place that there. And then my function is x squared minus 2x plus 2. And I forgot the plus somehow. Plus, thank you, 2. All right, and then move over and make sure you're in that little box and x. And then hit enter. And there's my integral, 4.66667, or 4 2/3. Okay, so that's number 5. Number 6, example 6, so math. Number 9, oh, but wait. It has to do with tangent. So let me go to my mode and make sure that I'm in radians. And fourth line down, I'm definitely in radians. Okay, as you can see right here, radian. I want it on radian, not degree. My answer will be wrong. Okay, so let me get out of that. All right, so my limits. Oh, wait. Anybody see the 3 and the plus 2? Okay, so what you want to do is really do 3 and then plus 2 and then hit math number 9. And then it'll look just like it does on your paper. So from 0 and then to pi over 3. So second pi divided by 3. Okay, pi over 3. And then tangent x. And then make sure that little box on the end has an x in it and hit enter. And then my answer is 4.386. Remember, in this class we do 3 decimal places. Oh, did I hit enter twice? Okay, that's it. Your homework is on the next slide. Please try to work on it. All right, see you in class.